want me to do any of these, I'll stop and we can do. But did we already look at this one here? 81? All right. And 82. 82, a dry mixture of hydrogen chloride. You know, if this were HCl aqueous, we'd call it hydrochloric acid. If it's just HCl gas, we'd call it hydrogen chloride. So dry, it's not, there's no water around, so they're just going to call it hydrogen chloride. It's a gas. And air is passed through a heated catalyst in the Deacon process for manufacturing chlorine. So what's going to happen is the oxygen is going to oxidize the chloride and hydrogen chloride to form chlorine. If the conversion is 63% complete, how many tons of chlorine can be removed from 1.4 tons of HCl? So, you know, this is a 1.4 tons of HCl is going to give a theoretical yield of chlorine. That theoretical yield of chlorine has to be cut down to 63%. Does that make sense? And so our actual yield is going to be less. So what we'll do is we use the 1.4 tons of HCl and I just go from, myself, I do this, I don't pay attention to this stuff here, you know, ton moles and all that other stuff. I just do 1.4 tons to pounds. So we go to pounds of HCl to grams of HCl, grams of HCl to moles of pure HCl. Now this is pure HCl, this is an HCl solution. This sort of HCl solution would be a mixture. And we'd have to use the composition of the mixture, but this is pure HCl. So we go to moles of HCl to moles of chlorine to grams of chlorine to pounds of chlorine to tons of chlorine. Now that's going to be the theoretical yield, and then we have to cut it down because we only get 63 tons of actual yield for every 100 tons of theoretical yield. And so we'll just cut it down right at the end. So this is what the book does. The book's going to skip some stuff, but we'll do that. And so 63 out of 100. If you want me to stop and do it and set it up, we'll just look at the problem. 83. Fluorides retard tooth decay by forming a hard, acid-resistant calcium fluoride layer in the reaction. So I think, did we do this one too? No?
Yeah.
Well, anyway, tin 2 fluoride, calcium hydroxide. And so this is what's in toothpaste. Tin 2 fluoride supplies the fluoride. Calcium fluoride is pretty insoluble. Fluoride, like if it was calcium chloride or bromide or iodide, it'd be soluble. But calcium fluoride is insoluble, and it's a pretty hard, resistant layer. If at the time of treatment there are 239 milligrams of calcium hydroxide on the teeth, the dentist uses a mixture that contains 355 milligrams of tin 2 fluoride. So we're given the amount of calcium hydroxide, we're given the amount of tin 2 fluoride. What do? This is what type of problem? This is a limiting reagent. And what do? We use which method? The smaller amount method. And so actually I think we went over this because the book did not use the smaller amount method. What did the book use? The book used a different method. The book used something called the comparison of moles method, which we talked about. So I wouldn't have done it like this. I would have calculated the yield from 239 milligrams of calcium hydroxide. I would have calculated the yield from 305 milligrams of this stannous fluoride. Then done it that way. But this is an alternate method that one can do is comparison of moles. It's actually comparison of amounts because it's not comparing moles, it's comparing milligrams here. So there's not enough tin 2 fluoride to protect the teeth. 84. In the recovery of silver from silver chloride waste, a certain quantity of waste material is estimated to contain 184 grams of silver chloride, AgCl. the treatment tanks are charged with 45 grams of zinc and 145 grams of sodium cyanide. Is there enough of the two reactants to recover all the silver from the silver chloride? So this is, if we go back to number 75, or 79, let's take a look at number 79. If you look at number 79, there aren't two reactants, there are three reactants. We have silver chloride, sodium cyanide, and zinc. And we're given amounts of three reactants. And so all we have to do is one additional step. And so we do this smaller amount method. In comparison to moles method would be a hassle with this. And so the smaller amount method is less work. And so what we do is we calculate the yield from silver chloride, and then we calculate the yield from sodium cyanide, and then we calculate the yield from zinc. And so what we have are, we're going to end up with three choices. Out of those three choices, which one is the smaller amount of product? And so it's just having one additional reactant. And so that's what makes this one an advanced problem. It's an advanced problem because we have to do three reactants rather than two reactants. And so here, 184 grams of silver chloride yields how much product? 45 grams of zinc yields how much product? The product being silver in this case. And 145 grams of sodium cyanide yields how much? And then we pick the smaller amount. In 1866, a young chemistry student conceived the electrolytic method of obtaining aluminum from its oxide. This method is still used. Delta H for this reaction, 1.97 times 10 to the third kilojoules for the reaction here. 2 aluminum oxides plus 3 carbons yields 4 aluminums plus 3 CO2s. The large amount of electrical energy required limits the process to areas of relatively inexpensive power. How many kilowatt hours of energy are needed to produce 1 pound of aluminum by this process? If 1 kilowatt hour is equal to 3.60 times 10 to the third kilojoules. So this is just dimensional analysis here. And so we want to do 1 pound of aluminum. So we would go 1 pound of aluminum. And then we ought to use this 453.6 grams. That could be, we're going to say exactly 1 pound of aluminum per pound. And then our delta H there, actually we need to go to moles. What's the molar mass of aluminum? 26.98. So this is just dimensional analysis. 26.98 grams of aluminum for every mole of aluminum. And then we're just going to use the delta H conversion factor. The delta H conversion factor is 1.97 times 10 to the third kilojoules per how many moles of aluminum? 1.97 times 10 to the third kilojoules for how many moles of aluminum? Four moles of aluminum. See from the equation. In fact, I think yesterday I made a mistake with one of the calculations. I forgot to divide or multiply by 2. Divide by 2. And then just one more. They tell us this. There's 1 kilowatt hour for every 3.60 times 10. Oops. 1 kilowatt hour equals 3.60 times 10 to the third kilojoules. Kilojoules, moles, aluminum, grams, pounds. Calculating like that. Let's see what their answer is. And so we just add this one additional conversion factor going from kilojoules to kilowatt hours. As long as we're told what the conversion is, it's fairly straightforward. In this case, we would be allowed 3 sig figs because of these two. So 2.30 kilowatt hours. This answers in the book. All right, nitroglycerin is the explosive ingredient in industrial dynamite. How much of its destructive force comes from the sudden creation of large volumes of gaseous products? Much of its, destructive force. So what happens is when nitroglycerin decomposes, liquids don't contain that much volume. Gases contain significantly more volume, so it forms like 12 moles of gas here, 10 moles of gas here, 6 moles of gas, a mole of gas. So it's a huge expansion in volume. It happens very quickly that leads to detonation. A lot of energy is involved in this. 6.17 kilojoules for this equation here. Calculate the weight in pounds of nitroglycerin that must be used in blasting operation that requires 5.88 times 10 to the 4th kilojoules of energy. So, this is just stoichiometry. So we got 5.88 times 10 to the 4th kilojoules. So we're going to go from kilojoules to moles. And so it looks like 4 moles of nitroglycerin for every 6.17 times 10 to the 3rd kilojoules. So that's exothermic. So what I do is I just change the sign. I'd write something though when I change the sign. So here it's 5.88 times 10 to the 4th kilojoules. That's the amount required. And then what we know is this. We needed that for every 4 moles of nitroglycerin. Nitroglycerin is kind of a long formula, so I'm just going to abbreviate NG, nitroglycerin, is going to give us plus 6.17 times 10 to the 3rd kilojoules of energy released or produced. So I can get rid of the negative sign and just write produced here. That tells me the direction it's going. It's going to be produced rather than consumed. This is the amount we need produced here. So it looks like we're going to need more than 4 moles because this energy is greater than that. And then from moles, we'll go to grams. We need the, then we'll go to pounds. We'll need the molar mass. Calculate the molar mass of that. 87, a student was given a 1.6240 gram sample of a mixture of sodium nitrate and sodium chloride. So we got a mixture. We don't, obviously you want to know the percent composition of the mixture, but this is going to be a mixture. There's a good mixture that contains sodium nitrate. What's the formula for sodium nitrate? NO3. And what's the formula for sodium chloride? NaCl. Once I asked somebody what the formula for sodium chloride is, and they told me SOCl for sodium chloride. I mean, it makes sense logically because sodium you'd like to have SO, but I think most people don't. NaCl. Asked to find the percentage, so we don't know, what the percent of each is. How much of each we have. It might be 50-50, but the percent composition is unknown. It doesn't have to be 50-50. A lot of people assume it's a 50-50 mix. They, for some reason, they always say, okay, half of it is the sodium nitrate, the other half is sodium chloride, but who's saying it's a 50-50 mix? Nobody said that. She dissolved the sample and added a solution that contained excess silver nitrate. So are both of these soluble? Yeah. So both of these are soluble. So if we add water, then what's going to happen? Well, if I add water, then I'm going to get sodium nitrate AQ and sodium chloride AQ. This is solid. Here, this is solid. And so we know that it's going to contain sodium ions, nitrate ions, and chloride ions, and water molecules as well. And added a solution that contains excess silver nitrate. So what we're going to do is we're going to add in excess silver nitrate to this. Nitrate salts are all soluble too. That's excess. Excess silver nitrate is going to contain silver ions and nitrate ions. So what we're going to do is we're going to have a mixture. We're going to have a mixture of silver ions, nitrate ions, sodium ions, nitrate ions, and chloride ions. Do you see a favorable ion combination there? What ions like each other?
Silver and chloride.
Silver and chloride. Those will react. Silver and chloride will react to form a precipitate of silver chloride. The other ions are just going to stay sodium ions, nitrate ions. Stay. Those are spectators. The silver ion precipitated all of the chloride ion in the mixture as silver chloride. It was filtered, dried, and weighed. Its mass was 2.056 grams. So basically we have to isolate the silver chloride, clean it and isolate it. And so in the end, if we clean it and isolate it, then and dry it, then they got the 2.056 grams of silver chloride. What was the percentage of each compound in the mixture? And so here, when we do percent composition, so what we want is we want a percent in the original unknown. We want the percent sodium chloride, and we want to know what the percent sodium nitrate is. And so what we have to realize is that all the chloride in the original sample, ends up here. And so there are two ways to do this. One way is, well, rather than doing it ions like this, we could do like this, double replacement. Silver nitrate is not going to react with the sodium nitrate. You know, silver nitrate and sodium nitrate yields NR. However, silver nitrate with the sodium chloride will react. And it's going to form silver chloride plus sodium nitrate. Silver chloride is a precipitate that's going to be the driving force for this metathesis reaction. And so what we see is that there's going to be a 1-to-1 mole ratio between silver chloride and sodium chloride. So we can figure this out here. The percent sodium chloride in this mixture is going to equal the grams of sodium chloride over the total grams of mixture times 100%. Okay, the grams of mixture is given. It's a 1.6240 grams of mixture. And so all we need is the grams of sodium chloride. The grams of sodium chloride, we're going to get this from stoichiometry. Get it? Because we can figure it out based on how many grams of silver chloride we produce. We'll go from grams of silver chloride to moles of silver chloride, moles of silver chloride to moles of sodium chloride, moles of sodium chloride to grams of sodium chloride. And so let's do it here. 2.056 grams of silver chloride. And then I need the molar mass of silver chloride. And so the mass of silver is 107.87. Silver is 107.87. Chlorine is 35.45. And so what does that give us? So it gives us 143 point. Okay, so 1 mole of silver chloride is 143.32 grams. And then it's a 1-to-1 mole ratio. 1 mole of sodium chloride for every 1 mole of silver chloride. And then sodium is 22.99. Chlorine is 35.45, 57, 58 point. 58.44. 58.44 grams of sodium chloride per mole of sodium chloride. So this is just standard stoichiometry. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. Straight stoichiometry. That'll give us the grams of sodium chloride that we need for the percent composition. So what does that come out to here? 2.056 divided by 143.32 times 58.44. 0.838. About 4 sig figs. 0.83835 grams of sodium chloride. And then we'll take this number and then plug that in up here. And divide it by 1.624, divided by 1.624 times 100. 51.6. 51.62, 4 sig figs, so 51.622% sodium chloride. And the rest is sodium nitrate. And so 100 minus this is 48.377%. So I'm going to get, for the sodium chloride, 51.62%, and then the rest is sodium nitrate, which would be 48.38%. Let's see how it looks. Your book did it a little differently. Your book calculated the grams of sodium chloride here. So we go from grams of silver chloride to moles of silver chloride, moles of silver chloride, moles of sodium, to grams of sodium chloride. And then your book said, well, the total weight of the mixture is 1.624. We know how much sodium chloride we have, so the rest is going to be sodium nitrate. So we get grams of sodium nitrate. And so the percent sodium chloride would be the grams of sodium chloride divided by the grams, total grams, grams of mixture times 100. We get 51.59. The slight difference due to rounding. So yeah, due to rounding, it's like. And then I just took 100 because this is only 2-component mixture. If it were multi-component, I'd do it like this. Let's say there are 3 components, I would do it like this. Grams, grams, grams. 4-component, I'd do it like this. 2-component, we know that the 2 components have to add up to 100%. Anyway, these 2 should add up to 100%, which they do.
How would you do 3?
The 3-component, I would do it like they did it. Here is like, for example, if there are 3 components in the mixture, A, B, and C, this mixture, then the percent A would be equal to the grams of A over the total grams times 100%. And And then normally I wouldn't calculate the others because the two component is the percent of A plus the percent of B has to equal 100%. But a three component mixture, then A plus B plus C would have to be. And so I have too many unknowns. And so what I do for percent B is I take grams of B over the total times 100%. And then for C, I wouldn't bother calculating it. I just say these three things have to add up to 100%. So C, I would get like this. I take 100% minus the percent A minus the percent B. That should give me the percent C because A, B, and C have to add up to 100%. And so I probably wouldn't do the last one. It's a rounding error. Rounding error make them not add up to 100%. Does that make sense? You could do all three like this. For example, this is one way of calculating C. The other way, or you just do it by this. Percent C is equal to the grams of C over the total grams times 100%. So you could do all three exactly the same way. Oh, what was that?
The total would be the mixture, right?
Yeah, the total is the mixture, which would be 100%. We're doing percentages, so we're just trying to get more familiar with percentages right now. A researcher dissolved 1.382 grams of impure copper. And okay, impure copper is a mixture. It's a mixture of copper and other impurities. In nitric acid, reduce the solution of copper to nitrate. So, what we have here is we have this. We got some copper solid plus other stuff. And we have 1.382 grams. This is the total, right? 1.382 grams total. So if I want the percent copper in here, the percent copper is going to equal the grams of copper in this. We got to figure out how many grams of copper there are in here, divided by the total. The total is 1.382 grams of total mass times 100%. Let's say if I did this and it came out to 1.382 grams of copper, then it's 100% copper. That's what we'd expect. But if it's anything less than 1.382, then it's not pure copper. And so, if we want to figure out what the composition of this mixture is, that's what we're often interested in. What is the composition of the mixture? You know? Well, the way this is analyzed is that nitric acid is added to this, and all the copper is converted into copper-2 nitrate. The solution went through a series of steps in which the copper-2 nitrate was changed to copper-2 hydroxide. And so that's pretty easy. Add sodium hydroxide to it, and then to copper-2 oxide, and then to a solution of copper-2 chloride. This was treated with an excess of soluble phosphate, precipitating all the copper in the original sample as pure copper-2 phosphate. The precipitate was dried and weighed. Its mass was 2.637 grams. Find the percentage by mass of copper in there. Okay, so this goes through a whole bunch of steps. But what we have to do is we have to assume that in each step we don't lose any. So there's 100% yield from one step to the next step. And so it doesn't matter. Of course we'd like all the balanced chemical equations, but it doesn't matter as long as we know what happens to the copper. And so we start off with copper metal like this. And that copper metal, all the copper in the copper metal ends up in copper-2 nitrate. And so no copper was lost. And so all this ends up here now. So 100% yield, no lost copper. If there's side reactions and there is some loss, then our calculation is not going to be so good. And so we're just going to assume 100% yield. Assume 100% yield. Okay, and then this was converted into what? It was changed to copper-2 hydroxide. And so what we have to do is we have to assume that all the copper ends up here. We didn't lose any. And then from copper to hydroxide, it's converted into copper oxide. Just heating it will do that. And so we end up with copper 2 oxide. And again, the same thing has to happen. We have to have 100% yield here for this to work. And then, which is possible here. You know, it's possible if you don't try to isolate it and separate it. You just keep going. And then the copper 2 oxide is converted into copper 2 chloride. And so all the copper ends up here in copper 2 chloride. And then we end up with copper 2 phosphate. And so again, all the copper has to end up here. And so basically, all the atoms of copper that we started out with end up here. So for example, if we started off with 1/2 gram of copper, then in this we have to have 1/2 gram of copper, right? Because we didn't lose any atoms. We didn't gain any atoms. Atoms were neither created nor destroyed. And so however many grams of copper in here, all that copper came from the original copper metal. And so what we can do is we can make up, we're going to make up a shorthand equation for this. And that is, this is going to be based on the formula. And so how many grams of copper 2 phosphate? Well, we got 2.637 grams of copper 2 phosphate that form. 2.637 grams of copper 2 phosphate, solid ends up here. All right, so what we want to do is we want to work backwards. We're going to work backwards. We're going to ignore all these. I'm going to ignore all this. And I'm just going to say, well, however many grams of copper there are here, that's here. And so there are 2 ways to do this. One is this, I can use the, this. Well, let's first figure out the mass of copper 2 phosphate. So there are 3 coppers. And so what's the molar mass of copper? Let's just get the periodic table there. 63.55. 63.55 times 3 equals 63.55 times 3. 190.65. We have how many phosphorus? 2 phosphorus, 30.97. 30.97 times 2. 6194. We have 8 oxygens. 16.00 times 8. 128. Technically, we're not allowed that, but we'll just go with it. 5 4s, 9, 15, 8. Oops, did I screw that up? 0, 1, 8, 9, 9, 15, 17, 379, 59. There are 2 ways of doing this. One way is I just do it like this. You know, I do my grams to moles. So we'll go moles of copper 2 phosphate is 379.59 grams. Copper 2 phosphate. And then what I'm going to do is I'm going to use the mole ratio from the formula. That is, there are 3 moles of copper for every 1 mole of copper 2-phosphate. This is from the formula. Three moles of copper, 2 moles of phosphate. Well, we need the grams of copper, so let's go to grams of copper, which will be 63.55 grams. All right, so let's go ahead and calculate it. It comes out to 2.637 divided by 379.59 times 3 times 63.55. And that gives me 1.324 grams of copper. So in 2.637 grams of copper 2-phosphate, we have 1.324 grams of copper. That's one way of doing it. The other way of doing it is by percent composition, by mass. So if we do percent composition by mass, or calculate percent comp by mass, and then use that. And so if I look at the composition here, I have 190.65 grams of copper. So 190.65 grams of copper for the total, out of the total, 379.59 grams total. The total is for the copper 2-phosphate times 100%. And so what does that give us? 190.65 divided by 379.59, 50. So it's 50.22% copper. Actually, I'm allowed more sig figs. I'm allowed 4 sig figs. 50.225% copper by mass. So if I know it's 50.225% copper, this compound, I'm just looking at this compound, copper 2-phosphate, then the alternate way of doing it is like this. Or I go 2.637 grams of copper 2-phosphate times 50.225 grams of copper for every 100 grams of copper 2-phosphate. So what does that give us? Times 2.637 divided by 100. I've got to redo it. 1.324 grams. Actually, I'm allowed 4 sig figs. 1.3244 grams of copper. That's the alternate way of doing it. The alternate way of doing it is more work, right? Because we have to calculate the percent composition by mass for the copper 2-phosphate, but in reality it's not more work because the percent by mass, we could look that up easily. I mean, if I go copper 2-phosphate, percent by mass is something that's usually given in the data here. Percent by mass composition. Wasn't given in the data. Normally when you buy chemicals, they'll tell you molar mass like this, percent by mass composition. surprised they didn't tell us. Well, in a lot of chemicals, they will tell us the percent by mass composition, but unfortunately not for copper 2-phosphate. I should look. All right, then we go for the percent copper in our original. And so we got to keep track of all these percentages. So if we look at the percent copper in the original sample, then this is what we're going to have. The percent copper in original sample is, we got 1.3244 grams of copper over 1.382 grams of sample total, comes to 100%. And this copper turns out to be, let's take a look, 1.3244 divided by 1.382 comes 100, 95.83. 95.832% copper. So how did they do it here? How they did it was they went from the grams of copper 2-phosphate to moles of copper 2-phosphate. And then they used the chemical formula here. You know, there are 3 moles of copper, 3 coppers for every 1 copper 2-phosphate. So 3 moles of copper for 1. So that's not from a balanced chemical equation. That's just from the formula itself. The formula itself is a mole ratio. We learned earlier. Chemical formulas are mole ratios. And then they went to grams of copper here. And then they calculated the percent copper here by taking the grams of copper divided by the grams of sample times 100%. 95.59%. Why are we off? 0.637. Molar mass. My molar mass is off.
Your math is wrong.
My math is wrong? Okay.
Yeah.
What is it, the molar mass? 380?
Yeah, 380.
Yeah, all right. I made a miscalculation here. But we're off. This is a little bit more than, round off error. They got 95.59. Mine's 95.83. That's a significant difference. So I was thinking I must have made an error. That's fine. And so this would be 380.59. Yeah, 380. I lost one, and so we need to put that in here. Sorry. It's going to change the answer. Anyway, we should always double check our calculations. I don't double check if the answer's here. I'll just look and compare, see what the answer is. So I think if we correct that, it should be the same number. '89. What mass in grams of magnesium nitrate must be used to precipitate as magnesium hydroxide? All the hydroxide ion in 50.0 milliliters, or 17.0% by mass sodium hydroxide, the density of which is 1.19 grams per milliliter. The precipitation reaction is, okay, I wouldn't have given you the precipitation reaction. I would have expected you to be able to figure that out. We'll go ahead and write that in here. All right, so I'm going to write it differently here. I'm just going to write magnesium nitrate first. Magnesium nitrate, it doesn't matter which one you write first, plus 2 sodium hydroxide. This metathesis reaction yielding magnesium hydroxide. solid plus 2 sodium nitrate. So what we want to know is we want the grams of magnesium nitrate. That's our goal, is to figure out the grams of magnesium nitrate. So in order to get the grams of magnesium nitrate, we need the moles of magnesium nitrate. In order to get the moles of magnesium nitrate, we're going to need the moles of something else. What is that something else going to be? Something else is going to be sodium hydroxide. Okay. And so we need the moles of sodium hydroxide. Well, if we want the moles of sodium hydroxide, then we're going to need the grams of sodium hydroxide. But what do they give us here? They give us 50.0 milliliters of a mixture. It's sodium hydroxide solution. And then they tell us that the solution is 17.0% by mass sodium hydroxide. And so what does that mean here? 17.0% by mass. How am I going to write this? Well, it's by mass, so that means 17.0 grams over 100 grams of what? Yeah, 17.0 grams of pure sodium hydroxide for every 100 grams of sodium hydroxide mixture, the mixture we call solution. So in every 100 grams of this sodium hydroxide solution, I have 17.0 grams of pure sodium hydroxide. The rest would be water. It'd be 83 grams of water and 17 grams of sodium hydroxide. But here I have milliliters of sodium hydroxide solution. I don't have grams. I need grams of sodium hydroxide solution, but they give us one more. They tell us the density of this sodium hydroxide solution. And so I know the composition and I know the density of this. The density of this is 1.19 grams per milliliter. Grams of what? No. If I just wrote sodium hydroxide here, I'm going to make an error. I should write sodium hydroxide what? Solution. You see, the problem is we're dealing with pure sodium hydroxide and mixture of sodium hydroxide. So we have to be very careful how we label it, because if we just write sodium hydroxide, we might mistake that for pure sodium hydroxide. It's not. This is not the density of pure sodium hydroxide. This is the density of the sodium hydroxide solution. So it's going to be 1.19 grams of sodium hydroxide solution per milliliter of what? Sodium hydroxide solution. That's like the density of water. The density of water is 1 gram of water per milliliter of water. Density is it's always the same on the top and the bottom. Can't be different. So we're going to just use dimensional analysis. Basically, we want to get grams of pure sodium hydroxide. We don't want grams of solution. We want grams of pure sodium hydroxide. So this is the way we're going to do it. We're going to start off with milliliters of sodium hydroxide solution. So we have the milliliters of the mixture. But we can't go from milliliters to grams of sodium. We're going to go from milliliters of sodium hydroxide to sodium hydroxide solution to what? Well, this one will convert milliliters of sodium hydroxide solution to grams. So we could just use this one. So we'll go from milliliters of sodium hydroxide solution to grams of sodium hydroxide solution. And then once we get to grams of sodium hydroxide solution, we'll use this one to go from grams of the mixture of sodium hydroxide solution to grams of pure sodium hydroxide. And so this is it. So this is just standard stoichiometry. The reason this is an advanced problem is because we have to do 2 extra steps. said, but the two extra steps, you know, individually taken alone aren't that hard. And so, so we'll just string everything together. We have 50.0 milliliters of sodium hydroxide solution. And then the density is 1.19 grams of sodium hydroxide solution per milliliter of sodium hydroxide solution. So milliliters of sodium hydroxide solution cancel. That leaves us grams of sodium hydroxide solution. Then we'll go 17.0 grams of pure sodium hydroxide for every 100 grams of sodium hydroxide solution. So grams of sodium hydroxide. So now we're no longer in the mixture, but now we know how many grams of pure sodium hydroxide there are in this 50 milliliters. If I stop here, that will tell me how many grams of pure sodium hydroxide are dissolved in that 50 milliliters. But I'm not going to stop here because once we're here, I got grams of A, so I'll go to moles of A. And so sodium hydroxide, well, sodium is 22.99, oxygen 16.00, hydrogen is 1.01. So this is going to be 0, 0, and that's going to bring that up here to 0, and then 40, 40.00. And so 1 mole of sodium hydroxide weighs 40.00 grams. So that takes me to moles of A to moles of B. It looks like a 2-to-1 ratio here. And so 1 mole of magnesium nitrate for every 2 moles of sodium hydroxide. And then finally, molar mass of magnesium nitrate. So magnesium, take a look at the molar mass periodic table. Here's my periodic table. There's 24.31. Oh, I might need a better periodic table than that. Let's see if there's a better one. Go 24.31. Okay, and then we have 2 nitrogens. 2 nitrogens would be 2 times 1401. Okay, so it's going to be 24.31. 28, 2, and then 6 oxygens. 6. 16, 48, 96, 3, 18, 148, 33 is what I got. 148.33 grams of magnesium nitrate per mole. That's how many grams should be required to precipitate out all the sodium hydroxide, the hydroxide after that. Let's see what they did. See, I like to label it more than they do. It's like sometimes I get so they went from milliliters of solution to grams of solution. Grams of solution to grams of pure sodium hydroxide. Grams of pure sodium hydroxide to moles of pure sodium hydroxide. From moles of sodium hydroxide to moles of magnesium nitrate. And then finally, moles of magnesium nitrate to grams of magnesium nitrate. And they end up with 18.8. You get 3 sig figs. And so it's just a standard grams of A, moles of A, moles. We just had to do some extra steps with grams of A. We aren't given it directly. Number 90, if a solution of silver nitrate is added to a second solution containing a chloride, bromide, or iodide, the silver ion, well, silver ions love chloride, bromide, and iodide, right? Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury, so silver likes those. If excess silver nitrate is added to a mixture of the above halides, these are called halides. Chlorine, bromine, and iodine are called the halogens. And if we're looking at the ions, chloride, bromide, iodide, those are called the halides. It will precipitate them both or all. And it will precipitate all of them, as the case may be. The solution contains 0.230 grams of sodium chloride and 0.771 grams of sodium bromide. What is the smallest quantity of silver nitrate that is required to precipitate both halides completely? And so what we're going to have is we're going to have sodium chloride and sodium bromide. And so let's look at them separately. So for example, sodium chloride. Smallest quantity of silver nitrate. So we're doing sodium chloride plus silver nitrate. Sodium chloride plus silver nitrate yields what? Yields sodium nitrate and silver chloride. Here. So let's just focus on the sodium chloride. If we have 0.230 grams, 0.230 grams of sodium chloride, then we'll go from grams of sodium chloride to moles of sodium chloride. Moles of sodium chloride to moles of silver nitrate. Moles of silver nitrate to grams of silver nitrate. And so this is how many grams of silver nitrate is required to precipitate out all the sodium chloride. Here, this is just a standard, grams of A, moles of A, moles of A, moles of B, moles of B to grams of B, standard calculation. And so we can do this calculation pretty quickly. 0.230 grams of sodium chloride. Then we'll need the molar amounts of sodium chloride, which I calculated earlier, but I forgot it. 2299 for sodium, 35.45, so 58.44. So a mole of sodium chloride is 58.44 grams. So grams of sodium chloride and moles of sodium chloride. Moles of sodium chloride and moles of silver nitrate. So it's a 1-to-1 mole ratio. 1 mole of silver nitrate per 1 mole of sodium chloride to grams of silver nitrate. Silver nitrate. You gotta erase that one. Do you have that in your notes? Some things, if you feel comfortable with calculating these molar masses, the one thing that can help you speed things along. This is if you feel comfortable. If you need more practice, then get more practice. But you could look it up. The molar mass of silver nitrate is 169.87. So I know I can do these. It's just busy work. And so if it's just busy work, then I'll just look it up. 169.87 grams of silver nitrate per mole of silver nitrate. But the thing with busy work is this. It depends. On certain ones, you want to calculate them because you want to memorize the numbers and you want to be able to do them quickly. But it depends on how often do you do silver. Like if it's, for example, a carbon, hydrogen, oxygen, nitrogen containing compound, I'll do those by hand because I want to memorize those. Like carbon, the more you use it, the more you remember it. So carbon's 1201. Hydrogen's 101. Nitrogen, 1401. Oxygen, 1600. If it's involving these, you want to use them because those ones you want to memorize those numbers and you want to do them quickly. But silver you don't use as frequently as those. So for this, I may or may not do it. Although silver is kind of common. I mean, it's 143.32, was it, or 33? See, I don't have it memorized. Sorry, silver is 107.88. 107.87. Silver chloride's 143. 107.87. That's silver. And then we have nitrogen, 1401. 3 oxygens is 48. So we could do it. But I'm going to save some time here. For your homework, you might be able to save some time, but again, it's useful to get more practice.
Over here is filled with carbon dioxide.
So let's calculate how many grams are required to precipitate out the sodium chloride. So 0.23 divided by 58.44 times 169.87. 0.6685. 0.66. About 36685. Required for sodium chloride. The problem with this particular thing is people try to combine it into one stoichiometry. What we'll do is we'll do 2 separate stoichiometry and then add the silver nitrate. So this is the amount of silver nitrate required to precipitate out the sodium chloride. And what we're going to do is we're going to do a separate calculation with sodium bromide. This is going to yield silver bromide, which is also insoluble precipitate. And so what we want to do is we want to figure out how much silver nitrate is required for this. So we're going to start off with 0.771 grams of sodium bromide. And then we'll just go to moles of sodium bromide, then to moles of silver nitrate, to grams of silver nitrate. And then we repeat the calculation. We determine how many grams of silver nitrate. Now to precipitate out both of them, we'll have to combine the silver nitrate. So we take this silver nitrate plus that silver nitrate, and that's the total amount of silver nitrate required to do these 2 reactions. So let's see how the book did it. Yeah, the book did it the same way, basically. They calculated how much silver nitrate is required for the sodium chloride, how much silver nitrate is required for the sodium bromide, and then just combine them. So they got 0.669 grams for the sodium chloride, and then they got 1.27 grams for the sodium bromide. Add those up, we get 0.94 grams. Some people try to do this. Some people try to do it like this. They go, well, if it's a mixture, it's going to react like this. We're going to take chloride plus bromide plus 2 silver nitrate. But there's a major problem with doing it like this. Do you know what the major problem? Because a lot of people want to try to combine it. Let me combine it like this. Sodium chloride plus sodium bromide plus 2 silver nitrates yields silver chloride plus silver bromide plus 2 sodium nitrates. What's the problem with doing it like this? There's a major problem with doing it like this. A lot of people try to do it like this because it's a mixture, and the mixture contains both sodium chloride and sodium bromide, so they try to do it like this. But this absolutely doesn't work. This absolutely doesn't work because, well, the reactions do work, but what they're assuming is this. If we write this equation, then the ratio, sodium chloride to sodium bromide ratio is 1:1. That is, it's a 50-50 mix. Does it have to be a 50-50 mix? If we have a mixture of sodium chloride and sodium bromide, must it be a 50-50 mixture? Or can it be any proportion we want? If you have salt water, does it have to be 50% salt and 50% water? I'd like a salt water. Well, that's 50% salt, 50% water. Does it have to be? No. If you know that air is composed of oxygen and nitrogen, does it have to be 50% oxygen, 50% nitrogen? It isn't. And so if we have a mixture and we do this, then automatically it's a 50-50 mix because we wrote it as a 50-50 mix. You know, this would be written, this would be what? This would be a 75% mix. 75% sodium chloride, 25% sodium bromide by moles. By mass, it's totally different. Do you want to do that? Do we know what the mixture is? No, we don't, so we do it separately. And so, this is wrong. A lot of people are tempted. Well, you know, a lot of people are tempted to do that. But they wrote two separate equations here. Equation 1 and then equation 2. Treat them separately. Formula reviews. Oh, in case you're studying. Well, we know that. What's this first one called? Magnesium hydroxide. What's this? What time is it? Oh, I went over time. All right, let's stop here. We're going to take a break.